Number patterns revisited. Linear, quadratic, and cubic patterns. In our study of algebra, we discovered that we can identify patterns in certain number sequences by calculating differences. The sequence -4, 0, 4, 8, 12, ... has a first difference of +4. So we can see our sequence is -4, 0, 4, 8, and 12. And to get from -4 to 0, we add 4. To get from 0 to 4, we add 4. To get from 4 to 8, we add 4. To get from 8 to 12, we add 4. So it creates the formula Tn equals 4n plus a, where n is equal to 1, 2, 3, ... etc. Therefore, if n is equal to 1, then term 1 is going to be 4 multiplied by 1 plus a, which is equal to -4. Because we know the first term here is -4. So we're going to have 4 plus a equals -4, and solving for a, we'll have a is equal to -8. Therefore, a constant first difference gives rise to an arithmetic or linear pattern, Tn equals 4n minus 8, where the a is -8. Now don't get confused and think that the a represents the first term, because that's what we're used to. It's just a letter to represent the number at the end. So this could be plus b, plus c, it can be whatever you want. So this is the Tn formula that will generate any term in the sequence. Don't mix this up with the function. This is not the function of this formula or this sequence. This is not the function. The function of this sequence would be 4x minus 4. f of x equals 4x minus 4, where the 4 is the slope, the number stuck on to the x, the coefficient of x. So the first difference will give us the slope of the line. And term 1 is our y-intercept. So this line will cross the y-axis at -4. So don't mix up the function of the sequence with the nth term of the sequence. The nth term will generate any term for you. But if we were to get the 0 term, so if we were at -4 and we were to subtract 4 and get the term 0, the term before the first term, we would get -8. So now we have another sequence, 7, 17, 31, 49, and 71. As the following table indicates, the sequence 7, 17, 31, 49, 71, ... does not have a constant first difference. We can see the first differences are 10, 14, 18, 22. Therefore, this sequence is not linear, and it would not represent a line, a straight line on a graph. So then we have a look at the second difference. To get from 10 to 14, we add 4. To get from 14 to 18, we add 4. To get from 18 to 22, we add 4. So the second difference is 4, making it a quadratic sequence. So this would look like a U-shaped graph if we were to draw it out on a graph. A constant second difference indicates a quadratic, so an n squared pattern, in the form of an squared plus bn plus c. Consider Tn, so the nth term, equals an squared plus bn plus c for all values of n greater or equal to 1. So before I explain this slide, I just want you to note that the plus c here is incorrect. That shouldn't be there. I'm going to delete that now. So this is taken from your book. So just to note that the plus c for each of the first differences should not be there. So I'm going to delete that now. Okay, so the following table evaluates the first and second differences in terms of a, b, and c. So for term 1, we have a plus b plus c. For term 2, we have 4a plus 2b plus c. For term 3, we have 9a plus 3b plus c. For term 4, we have 16a plus 4b plus c. And for term 5, we have 25a plus 5b plus c. So this a here really has an invisible 1 stuck onto it. And we know that 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So for term 6, the coefficient of a should be 36, because 6 squared is 36. For the b's now, we know that this b really has an invisible 1 stuck onto it. And notice that the pattern is, for the b's, is 1, 2, 3, 4, and 5. So for term 6, the b term should have a coefficient in front of it, should be a 6. So it should be 6b. And then we have plus c, plus c, plus c, plus c, and plus c. So again, for term 6, there should be a plus c at the end of it. Now, to get the difference between terms, so to get from 1a to 4a, we add 3a. And to get from 1b to 2b, we add 1b. Then to get from 4a to 9a, we add 5a. And to get from 2b to 3b, we add 1b. To get from 9a to 16a, we add 7a. To get from 3b to 4b, we add b. And to get from 16a to 25a, we add 9a. To get from 4b to 5b, we add b. So the first difference in this sequence is 3a plus b, 5a plus b, 7a plus b, and 9a plus b. So you can see the pattern. You've got 3, 5, 7, 9. So we imagine the next difference would be 11a plus b. And then to get the second difference, 3a, to get from 3a to 5a, we add 2a. To get from 5a to 7a, we add 2a. And to get from 7a to 9a, we add 2a. So for the next difference, the next second difference, it would be 2a again. From this table, we can see that the second difference of a quadratic pattern of numbers is always 2a, twice the coefficient of n squared. Therefore, if the second difference is 4, then 2a is equal to 4, and half of 4 is 2. So the a term, a would be equal to 2. So therefore, Tn would be equal to 2n squared. So the a is 2, 2n squared plus bn plus c for n values equaling 1, 2, 3. So just showing you again where the 4 came from. So this is the sequence that this is based on. So this is just writing it out algebraically, but the sequence is 7, 17, 31, 49, and 71. So 4 was the second difference. So dividing 4 by 2 gives us the first part. So what goes in place of the a for our nth term for this particular quadratic sequence. So I've just put the sequence up at the top here so we can refer back to it when we need to. So we know what a is. A is 2. We worked it out because half of 4 is 2. So to find b and c, we're going to use simultaneous equations. So again, Tn is equal to 2n squared plus bn plus c. So we're going to let n equal to 1. So we're going to replace each of those n's with 1. And we're going to let it equal to 7 because 7 is the first term. So when n is equal to 1, our first term is 7. And simplifying, we get b plus c is equal to 5. So here we have an equation in terms of b and c. We're going to create another equation in terms of b and c now, and then we'll solve simultaneously. So we do the same thing, but then we let n equal to 2 this time. So T2 will be 2 times 2 squared plus b times 2 plus c. And we let that equal to 17 because term 2 is 17. So that's where the 17 comes from. So b times 2 is 2b. So we bring that down. We bring down the plus c. 2 squared is 4. Multiplied by 2 is 8. And 17 minus 8 is 9. So we have 2b plus c is equal to 9. And then we're going to take the equation that we just set up. So b plus c is equal to 5. We're going to write it underneath. And then we're going to solve. So we can change the signs on the bottom. So the c's will cancel. So you'll have c minus c will cancel. And 2b minus b will give us b. And 9 minus 5 will give us 4. So we've solved for b. We also know what a is. Now we need to find c. So we take one of the equations, it doesn't matter which, and we sub in b to find c. So if b is equal to 4, then we're going to have 4 plus c is equal to 5. So using this equation here. And solving for c, we get c is equal to 1. So now we know what a is, and we know what b is, and we know what c is. So we can sub them all into our nth term formula. So we have Tn equals 2n squared, because we got a to be 2, plus 4n, because we got b to be 4, plus 1, because we got c to be 1, for n values equaling 1, 2, and 3. So this is our nth term for this sequence here. So subbing in place of n, if we wanted the 10th term, for example, we'd swap the n's for 10 with brackets. So if you sub in, if you wanted to check if it actually works, let's say for the third term, we've 31. So 2 multiplied by 3 squared plus 4 times 3 plus 1 gives us 31, and so on. So this is our nth term for this quadratic sequence. The method of finite differences can be used to study patterns of numbers with higher powers. If the third difference is constant, we have a cubic pattern. So Tn is equal to an cubed plus bn squared plus cn plus d, etc. So the first difference, if the first difference is constant, the pattern is Tn equals an plus b. So that's for a linear equation or a linear function or a linear sequence. So a is equal to the first difference. If the second difference is constant, our pattern is Tn equals an squared plus bn plus c. So 2a is equal to the second difference. And if our third difference is constant, we get a cubic pattern. So Tn is equal to an cubed plus bn squared plus cn plus d. And the rule is that 6a is equal to the third difference. So dividing by 6 will give us the third difference. This is not in your formula book, but page 20 might help you remember. So on page 20, you have the roots of a quadratic equation. Ax squared plus bx plus c is equal to 0. And it looks very similar to an squared plus bn plus c. And this is obviously the format of a quadratic sequence. So you don't have it in your formula book to learn off. You do have to learn these off by heart, but page 20 of your formula book might help you to remember the one for a quadratic sequence.